Hey, what is up, everybody? Welcome back to this playlist on mathematics for engineering and analytics, and for whatnot, even I don't know. So, in the last session, we talked about, we started off with linear algebra after I gave you a TED talk about why I wanted to create this playlist. Basically, I just want to keep on doing math. So, that's also my own self interest when I'm recording these videos. We started with linear algebra that you see on your screen. We started with a few terminologies, just like we do in school, just so that for anyone who does not understand what a vector is, what a scalar is, what a matrix is, what a unit vector is, at least these definitions at a bare minimum you should know as you step into linear algebra, right? So let's now move on and carry forward our understanding on this topic with the intuition behind vectors and a few vector operations. Let me write it down. Intuitions behind vectors and vector operations, right? So that's something that we'll be looking at now. Intuitions behind vectors and vector operations. Important because, I mean, like I said, when you step into deeper topics like machine learning, deep learning, and maybe any engineering research problem that you're trying to solve, intuitions will try to make things easier to understand. Even when you're reading a research paper, if they're using pretty involving linear algebra, you'll figure out things really comparatively easier. Okay, so basically one term that I like, I mean, one term that should always strike you whenever you look at linear algebra is the term transformation. Okay, I mean, whichever computation you are doing, be it matrix multiplication, be it dot product, cross product, whatever, everything in some or the other way, it kind of transforms the original state of space to some final state of space, right? At least that's my understanding of things, and that's something that almost, I mean, if you are good at visualizations and graphics, if you draw the initial vector in a space and in the Cartesian axis, and you draw the final vector after some transformations or after some, let's say, a matrix multiplication, you'd see that it is the same initial vector but maybe squished around or maybe inverted or elongated or something. For example, a common transformation can be something like this. So you have this vector, okay, you have this vector, let me keep it in a box, and you apply some transformation, let me use a asterisk, and you see that the same vector, it transformed to this. So this kind of transformation is what defines linear algebra and matrix theory. Matrix theory, vector theory, these things, they lie in the heart of linear algebra. Let's start with the intuition behind what a vector is. Okay, what a vector is. Let's focus on this particular term. All right. So basically, let's start with a collection of numbers definition. Let's say we have 1, 1. We have two numbers and I've stored them as a vector. Like I told you in the last session, vector is a collection of numbers. Now, what would that mean in space? A vector is always associated with space, Cartesian space, or maybe you can call it the Cartesian axis. I mean, in other words, you can always draw a vector on a graph if they are easier. For example, at least this one I can draw on a graph. Okay, now let me make a box for a Cartesian plot. Suppose this is the box we have, this is the space we have, right? Now, this vector, let's say this is the x-axis and this is the y-axis. Okay, let me zoom in a bit. Okay, let's say this is the x-axis and this is the y-axis and this is the origin. An origin can also be called as a vector with no magnitude and no direction. So 0, 0, it's a point. Okay, now what is this vector? So if you move one a magnitude, so one step, so let's say this is 1, this is 2. Okay, and similarly this is also 1 and this is 2. Okay, so now if I move like this in the x-axis, so that first thing is always about the x-axis and the second term is about the y-axis. Let's keep our discussion to that point now. And now, if you this is the movement you do on the x-axis, and this is the movement you do on the y-axis. So basically, the first movement is one magnitude or 1 unit on the x-axis, and then you move on 1 unit on the y-axis. Okay, let's say this is 1 unit. Okay, 1 unit on the y-axis. So basically, if you now come to a point, this is the point you have come to after making these two movements, 1 and 1. So this, if you join with an origin, this is what this particular vector means. This red or maybe maroon vector that you see, this is also a vector, right? So this vector is what this particular definition of a vector means. Okay, so whenever you write a vector is 1, 1, you are basically, what you are trying to define is that this vector is nothing but this one, which is 1 unit on the x-axis and 1 unit away on the y-axis. Okay, now similarly, if you ask me about, let's say, some other color, let me pick, let's say this one, let's say 2, 1. How would you define that? And this is again x-axis and y-axis. 2, 1. What would 2, 1 mean in the space? So 2, 1, again, it's like moving 2 units on the x-axis, you come here, and 1 unit on the y-axis. It's the same tallness as this one, right? You come here. So if you join this point with the origin, so if this is vector 2 and this is vector 1, so this is vector 2. Similarly, you can keep on adding more and more dimensions. So basically, this vector has 2 dimensions, and that's why you need just 2 axes to plot it, 2 dimensions. Okay, and similarly, I mean, if you had just this one, 1, 0, if you had just this one, 1, 0, that would be this vector. And this is the same vector that we looked at in the last session. We call it a base vector. This is the base vector, I cap, j cap. This is I cap. Okay, this particular vector is I cap. So this vector can be called I cap. Okay, because the only magnitude whichever exists is in the x direction. And similarly, 0, 1, it is the j cap. All right. Now, if I ask you what is a vector multiplied by a scalar? Again, coming back to this particular definition, let me color it a bit. This particular definition, transformation, a vector is a transformation. Let's prove that. Let's prove how a vector is a transformation. Let's prove that by a simple visualization, and then we will move on to the next session, right? All right. So let me zoom it out a bit. I need a bit of space. Okay. Let me zoom it out. Yep, going down. So basically, what we want to look at is, what does vector multiplied by a scalar do? Vector multiplied by a scalar. And why this scalar term has come into existence, we will understand that now. Let me draw again. Let's start with a vector. For example, my vector v is, let's say, 2, 3. This is my vector, and my scalar is, let's say, 2. Okay. Now, if I draw space, let me draw space by a box again. Again, I need a bit of zooming out. Let me clear a bit of space. Now, again, now if I draw a nice little box here just to have some space for me, let's say this is our box. Okay. Now, the original vector is 2, 3. Let's draw it. So let's say this is 1, and this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7, and this is 8, and this is x-axis, and this is y-axis. Again, 1, 2, 3, 4, 5, and 6. Okay. All right. So now the initial vector is 2, 3. Again, moving 1 step and 2 step on the x-axis and 3 steps on the y-axis. So 1, 2, and 3 steps on the y-axis. So this is my initial vector v, 2, 3. So this is my v vector. Now, Ideally, when you do a vector multiplication, the V final becomes this one. Let me use a different color. The V final becomes this one. V final is every term gets multiplied by 2. So 4, 6. Okay. So 4, 6. So basically, if you have, let's independently draw this one, 4, 6. So basically 1 step, 2 step, 3 step, and 4 step. So this is the 4th step. So this vector will have this length on the x-axis, just drawing a dotted line for a demonstration, and 6 on the y-axis. So 1, 2, 3, 4, 5, 6. So basically at the top. Okay. Now, if I draw it from the origin, if I connect it from the origin, this will be the final vector. This will be the final vector. What I'm trying to say is this vector will also pass through the original orange vector V, and this will keep on continuing up to this point, V final. So basically, what are you observing from this point? That the vector V final is the same vector V, but it is stretched up to twice its length. So exactly what I meant when I said that a vector operation or a matrix operation, it's a transformation. So if you multiply the given vector with 2, the original vector gets stretched by twice. So that's why the term scalar comes into existence. Scalar is something that upscales or downscales, which is a transformation again, right? Transformation. The original vector. To prove it again, if I use the black color now, if I use the S dash, let's say 0.5, if I use the S dash as 0.5, again, multiplying S dash with the original vector would half the first dimension, which means the final vector would be 1, 1.5. So let's look at 1 is here and 1.5 is here. So again, this point lies on this particular vector. So basically V final second, V final 2, which is this one, is the same vector, original vector, orange one, halved from its original length. So we have verified when I said that a vector or any operation that you do in linear algebra kind of transforms the original state of space. That's exactly what is happening right now. Okay. So now when I say that 3 cap is nothing but this I cap multiplied by 3 times. So this 1, 2, and 3. So 3 cap is this vector. And I hope that intuition stays with you for the remainder of your lives. Happy learning. See you again in the next session.